Well, welcome back to our 8-bit computer build. And now that we have finished all the modules, it's finally time to build the last one, for this time at least, to build the control logic. And I have already placed some components here on this part here near the memory address register, and this part below here will have the ROMs for our microcode. This top part here will have some more registers that we'll need, that I'll explain in a bit in the schematics. A counter for our microtime, a multiplexer, and demultiplexers that I'll also explain with more details on the schematics. So let's get on to it, the schematics. These are the schematics for the control logic, and as I promised, we'll just explain real quick here what is going on this part of the build. Well, I'll start here on this register, the 74LS273. This register here, it takes as inputs the output of our instruction register that we built on our last video, and it looks like it's just latching the same values that already are in the instruction register. And why would we do that? Well, the reason for that is that if you look closely, we're actually using the inverted clock signal to latch this particular register chip here. And this means we are latching on the falling edge of the clock. And we do that because we want our control system here, our control will get the signals from not only from this register here, but also from other parts. But well, this part here, the instruction itself, these 8 bits, are coming from this register, and we want the control to have its inputs stabilized on the rising edge of the clock, when the rest of the computer is doing all the stuff it needs to do. So that means that also our instruction register, our main instruction register that comes before this one here, is latching on the rising edge of the clock. And if we would not use an intermediate register like this, what would happen is on the rising edge of the clock, we would latch an instruction, a new set of instruction, and immediately these values here would be inputting to the control logic, to the microcode, to the decoder, to the microcode decoder. And we could have all sorts of problems because the inputs of the decoder that we'll see in a bit, based on these EEPROMs, would change while the computer is executing something, and this could disrupt whatever the computer is doing. And we couldn't solve this problem by latching the instruction register itself on the falling edge of the clock, because remember, although all the latches on our computer are latching values on the rising edge of the clock, for some components, for example the buffers, the tri-state buffers, the 74LS245s, they simply enable, disable states. They're not synchronous to the clock. So that means if we would latch the main instruction register on the falling edge of the clock, we could be latching a value that's not anymore what the correct instruction that we would have to latch. So this intermediate register here serves for this purpose, to keep the address lines from the EEPROMs that decode or microcode very stable from the moment on the rising edge of the clock, on the moment that the computer is really doing something. And that's why we use this chip here. And I chose the 74LS273 and not the 173 or the 377, because this one differs from the 377 in a way that it has a clear signal. This is the pin number 1 here. We can clear it, and as I said, for the instruction it's important that we have this function here to clear the register when we want to reset the computer. And we could of course use 2 of the 74LS173, but not only would we have to wire 2 chips, but we would also not need the functionality it has, that is to enable its input. And this one here, the 74LS273, is always enabled. It always latches something on the clock pulse. And for us this doesn't matter, because the only thing it can latch is the instruction coming from the instruction register. So it will be fine. And we will use that. And this will feed the first 8 addresses of our EEPROMs that will decode the instruction. And we'll come back to this later. And of course we also will have 8 LEDs just to show whatever is this part here of the control instruction. On par with that, we'll have this second register here on the control logic, another 74LS173, that we will do the same, absolute the same function as the register we just explained, but for the flags coming from our ALU. Because for the same reason, the flags, the instruction register, the flags register, it's clock on the rising edge of the clock, and we don't want that on our instruction decoder. So this register here is inputs. It's a delay register as the first one that will latch on the falling edge of the clock. And this one is a 74LS173 because we just need 4 flags. And this is this part of the logic. And from our inputs, the carry, 0, negative, and overflow flags, just the carry flag is directly driving one of the control lines of the instruction decoder. And that's because we will have more than one instruction that we will need to look for the carry to do something. And so not only for the jump on carry instruction, we also have an add with carry or subtract with borrow, that's also a carry. And for this reason we need to pass this value just as it is to our instruction decoder. But the other 3, we don't need to access them at the same time. We'll just need to look at each one of them at a time, because we'll just implement those on jump functions. Jump if 0, jump if negative, and jump if overflow. So for that we feed the result from this intermediate register here on a 74LS153, that is a multiplexer. And on this multiplexer we'll use its inputs as 0 and S1 coming from the first 2 bits of our instruction, the least significant bits, to encode this flag that on a single output. And why do we need to do that? Well, we do that because we just have one address left on our EEPROMs, that are the 28C64s, although I have used the 256 here to represent them. We don't have address line 13 or address line 14 on the 28C64. I didn't want to bother to find the model for KiCad for that, because it's absolutely the same form and the same pins, and the only difference that on this 28C64 these 2 pins here are not connected, and that's what I represented here, no connection on these pins. But anyway, this last address bit that we have, we'll be using to get the result from this multiplexer here that will either represent the overflow, the negative, or the zero flag, depending on the instruction. So that means if we want to use this jump on overflow, jump on zero, and jump on negative, we will have to make sure that when we program our microcode, the instruction for these jumps starts with a 1, with a 1 on the least significant bit, or a 1 on the second least significant bit, so that we select properly what we want to look for. And the way it's done here, what is connected to the pin 11, which is the overflow, will get selected, if I'm not mistaken, when we have a 1 on S0, that is the least significant bit, and when we have a 0 on S1, and we have a 0 on S0 and a 1 on S1, we will select the second input, and we have both 1 on S0 and S1, we'll select the third bit here, that's the zero flag. And if we have both 0, we'll get 0. We'll select this line here that's connected to ground. So what we accomplish with that is, by encoding the instruction properly, we can select, then we can make the control logic aware of what flags we want to be looking for on this particular time. And of course we could have also gone with a larger EEPROM at the 28C256, for example. We will have then the 3 bits here free, and we could just feed all the flags directly. But I happen to have only the 28C64 on hand, and this is quite a ingenious way to encode the value. And this was an idea I took from James Bates, and I thank him for thinking about this. Well, what else do we got? There's 2 LEDs here to show the carry flag and the multiplexed flag that we got from our instruction. And these other 3 LEDs here, which are controlling the other 3 remaining lines that we haven't talked about, that comes directly from a 74LS161 counter. This counter here will be responsible to control the micro time, or for each execution cycle from each instruction. It will count. It can count. It has 3 bits, so it can count from 0 to 7, and we'll use that so we have the maximum of 8 micro instruction per instruction. And connected to that, I have here this demultiplexer, the 74LS138, that just serves as a visual of which part of the micro instruction are we executing. It just decodes the binary here to select each line at a time and light up one LED. In the 74LS138, it is all negative logic, so I have connected the LEDs to plus 5 volts, and they all get here also on the output, when they are not enabled, plus 5 volts, so all LEDs are off, and each selection pulls the pin to ground, so the LED will light up. What we also have here is the part to clear the computer. It's just a simple switch that will connect to 5 volts when pressed. And when we do that, it will send the clear signal to all the parts of the computer that have a clear, for example, the instruction register and the flags register outside from this control logic here. And we will also clear this intermediate flags register and intermediate instruction register. And we also borrow one inverter here that's free on the RAM module to create the inverted clear signal that we need on this part here, just to clear the counter that controls our micro time, but as well to clear the main program counter on our system. Continuing on the schematics here, we arrive finally on the part that we have our 3 EEPROMs that will hold our microcode, and they're connected in a way that the first EEPROM here controls 2 demultiplexers. And what we achieve with that is by using for each one 3 lines. These are the same demultiplexers used on the display for the micro time, the 74LS138. Using 3 lines each, we can control 7 outputs here, 7 control signals. And I say 7 and not 8 because one of them we will leave without a connection, because when we have here, in this case I have used also a negative logic. When we have all the bits from the demultiplexer input high, it will select this output 7, which is connected to nothing. And when we alternate the inputs here from then counting down from 6 to 0, we will select a different output. And remember, the 74LS138 is also negative logic, so and conveniently we are driving here all signals that are also inverted logic. So and I've chosen here exactly for this two demultiplexer here signals that are never to be on together. So it doesn't matter. The one drawback of using the demultiplexer is that we cannot select 2 of these outputs here at the same time. But for these that we're controlling here, it doesn't matter, because we're just controlling the inputs of our registers. That's register A in, B, C, D, program counter in, stack pointer in, instruction register in. So although we could input to more than one register at a time, we won't do that. We have no instruction that could benefit from this. And on this other demultiplexer here, we have the same, but for the outputs, the register A output, B, C, D, program counter output, stack pointer, and ALU output. In this case here ALU, but not instruction register. We don't have an instruction register out. And these are of course, in this case here, are emblematic that we cannot have 2 registers or 2 signals outputting at the same time. We would have a short circuit on our bus, a conflict. So this is more than clear that it's using the demultiplexer will have absolutely no impact on our instructions. And what we have here for the other more so to say direct approach, we have the memory address register in directly to the EEPROM, the micro time clear directly to the EEPROM. I'll come back to that later in just a bit. The hold signal, the LU in, the carry in, and from this point on we start having the positive logic here on our control signals. And if you notice, these LEDs here are all connected to ground, while the other ones were all connected to 5 volts, so that they would remain off while the output was high. That means disabled, and when enabling it with output low, the LEDs would go on. And this is the opposite. This is actually the more straightforward approach. When the signal is on, the LED is on as well. And for this part here we have the ALU control S0 to S3, the logic function selector, the program counter enable, RAM in, RAM out, and this last one here again is the negative logic, is the program memory, is the control for the logic to access program memory on the RAM. And as I said, we will come back to this micro timer clear signal that only that doesn't need to be fed to any external modules. It just clears the timer that controls the instruction, the micro instructions. And I could have used an OR gate to connect to the clear pin from the counter, but to save this chip, because I don't have any free, or I haven't used actually any OR gates on this build, but I also don't have any NAND gates available or anything like that. So what I did is join together one of the enables of the counter on pin 10 together with the load from the counter that's conveniently pin 9, and one is logic high or the other is logic low, and I have tied to ground all the inputs from the counter. So that means when the signal from the micro time clear, while it remains high, since this is a logic low, it will not load and it will enable the counter, so it will behave normally, it will count. As soon as the clear micro time clear signal arrives, that is a 0, as soon as this state here goes low, it means that I will disable the counter, it will stop counting, and I will load all zeros, effectively resetting the counter. Well, I guess that's it for this schematic, and what I also want to talk about now is the main schematic here that shows all the modules connected together. We have the LEDs connected to our bus and all the modules connecting to this same bus. That's our registers, and in case of the decimal displays, directly connected to register A. Register B here feeds directly on the ALU, and the instruction register feeds directly to the control logic. And of course we have all the signals, or all our control signals here, going to the respective modules that they need to control. And I guess that's it. We can start our build of this last module, and of course we'll have to then join our boards finally and properly connect the bus and do some testing. So let's get on to it.